The last topic covered in chapter 35 of your book is the idea of resolving power and the so-called Rayleigh or Rayleigh limit, Rayleigh criterion, different names for it. And I chose this background color because it was obnoxious. I hope you like it. First, I will refreshify your memory about the diffraction through a single circular aperture. Here is a laser beam incident upon a very small hole, a circular hole. Contrary to what one might expect, you do not see a mere circular pattern of light. You see these concentric circles. The only way to explain that is to regard light as a wave. We've been over that. That's the interference or diffraction pattern characteristic of a circular aperture. And the laser beam is an excellent approximation of a plane wave as it hits the hole there. There's some vocabulary we looked at. The very central bright spot, that's called the airy disk. And we talked about how you can calculate the angles at which the light intensity goes to a minimum. Yeah, this is actually, I'm realizing this is labeled poorly. Forget this maxima business. This is the angle at which the light actually drops to practically zero. You can use those angles to find the width of the airy disk. This is something I prepared in Python. In fact, I'll show you the script in a moment, but I told the computer to create a circular pattern of point sources, to send out waves from each one of those point sources, and then to look at the screen where the light falls. And at each point on the screen, you're looking at the screen. At each point on the screen, sum up the waves from all those sources within the source circle, then take into account the fact that they have different phases to find the total amplitude, square the amplitude to get the intensity. Here is the script that I used. I won't go into detail talking about this, but if you're curious, you can find it in a folder labeled best in another folder called Python scripts for 3C, and that link should be on Canvas. If it's not and you're interested, let me know. But you'll notice here that I've labeled the boundaries of the so-called central width, or the width of the airy disk here. So if this is the origin of my coordinate system, over here I'm at width divided by 2, negative width divided by 2. I've indicated that down here. There's a simple formula for that width. So let's review the geometry of circular aperture diffraction. Your plane wave is coming from over here. It diffracts through this small hole, circular hole, and on a screen somewhere over here. Of course, they've kind of rotated the intensity by 90 degrees so you can actually see it, but this would be a graph of intensity versus position. And this angle right here, in the diagram it's just labeled theta, but your book refers to it as theta min. That's the first angle at which the light intensity drops to a minimum. It's very easy to calculate. See, there's that ubiquitous ratio that we saw many times in chapter 33. Wavelength compared to slit width. In this case, it's a slit diameter, hence capital D. And that 1.22 is slightly different from the factor of 1 that you would see in a single slit diffraction. Now we're talking about not just a long rectangular slit, but a circular hole. So the formula comes out just a little bit different. Okay, now that's the angle that will give you the first minimum in intensity on either side of the center of the central maximum. So you could use the small angle approximation. Let's see here, theta is roughly the same as the tangent of theta, and the tangent of theta is y over L. So look, imagine a right triangle here, and the hypotenuse would be the distance from the hole to this point on the screen where you have your first minimum. So if you take y minimum, that's the coordinate of the first minimum, and divide by L, which is the distance from the hole to the screen, that would be the tangent of theta. That's basically equal to theta if you're measuring theta in radians. and that's where this formula comes from. Well, the obvious definition of the width of the Airy disk would just be twice that distance. So I've doubled y min, and then right here, instead of theta min, I've substituted this expression. And that's where this formula comes from in your book. This is the width of the Airy disk. That's the central bright spot in the circular aperture diffraction pattern. You should probably have that on your note card. Okay, well, in this chapter, chapter 5, we're not just talking about light diffracting through a hole. We're talking about light passing through lenses or mirrors, or reflecting off mirrors. So there's a description in your book of how you can think of light passing through a lens as a two-step process. First, imagine a circular barrier in front of the lens. The light has to first pass through that circular barrier. That's diffraction. And then it will be focused by the lens. So they've separated the two aspects of this process, first diffraction and then focusing by the lens. And truthfully, I find this challenging conceptually because the wave model of light and the ray model of light, they can be a little difficult to reconcile. You have to bring both to bear on the act of focusing light by a lens. And it doesn't have to be the lens of a telescope or the lens of a camera. It could also be the pupil of your eyeball. When light passes through the pupil of your eyeball, it first diffracts, but then it also passes through the curved surface of your cornea. It passes through the lens that's right behind your cornea. So you have to think about diffraction and ray tracing to make sense out of this. Now, this next assumption that your book makes, to me, this leaves a little something to be desired. Remember that there's a specific direction in which all of the rays coming from this circular, all of the waves coming from this circular aperture would interfere destructively. I'll go back a couple slides here. This particular angle, theta 1 or theta min, that is the direction in which all of the various waves coming from the circular hole would arrive at the screen out of phase. That's destructive interference. You would get a dark spot. And your book is suggesting that that direction won't change, even if you put a lens in front of the aperture. See, to me, as soon as you've placed a lens in front of the aperture, you've made this considerably more complicated. It seems like you'd have to go back to the drawing board to figure out in which directions you would have destructive interference. But they're saying, if you look at this central ray, since it passes through the center of the lens, it's undeviated. Remember, it's rays that hit the lens away from the axis, which actually get refracted the most. Any ray that passes through the center should be undeviated. And they're suggesting that since that ray is not bent, it should still give the direction in which you'd have destructive interference. So I find that a little unsatisfying. I'm going to go back to my notes here. In my mind, if you wanted to give a more thorough explanation of how to, let me back up here. If you wanted to give a more thorough explanation of what interference or diffraction pattern you could expect on the other side of the lens, you would want to do this. Imagine a whole bunch of point sources. Remember the Huygens principle? And from each of these sources, imagine little circular wavelets coming out. And you'd look at the total path length from here to the screen. So pick some arbitrary point on the screen and ask, for all of these various waves which leave the circular hole and arrive here, do they tend to arrive in phase, out of phase, something in between? So you could look at the total path length here and compare it to the total path length for this wave, compare it to the total path length for this wave. In other words, actually calculate the phase of all the various waves arriving here and use that to determine the amplitude of the total wave. Previously, if you think back to chapter 33, all we had to do was imagine straight line paths from the aperture to the screen point. and we did a little bit of geometry. Remember that expression d sine theta that gave the path length difference? So this is definitely more complicated because the lens causes each of these waves to take a bent path on the way from the aperture to the screen point. And not only that, but the wavelength would change in here. Remember, because of the index of refraction, the wave's going to travel a little slower within glass. The wavelength will be shorter. But if you could somehow take into account all of those variables, you could still ask, what is the total amplitude here due to all these waves which are traveling slightly different distances? That wouldn't be too difficult to do with the computer. I'm sure that was done even in the 19th century using calculus and some clever tricks with integrals. So maybe I'll go into Python and try to actually produce the diffraction pattern over here, taking into account this lens that's in the way. But your book just suggests, let me go back to PowerPoint now. Your book suggests that the diffraction pattern still has the same angular dependence as it would before. The only new assumption we make is because you're passing this light through a lens, we know that the lens is going to focus the light at a particular distance from the lens. That's called the focal length. That's assuming the light is coming in parallel. Remember, the focal point is where parallel light rays get focused. So instead of some arbitrary screen, hang on a second, some arbitrary screen distance L, this could have been anything. Remember in lab, you could have seen that pattern if L was 1 meter, 2 meter, whatever you wanted. But now there's a particular so-called screen distance. It's the focal length F. So here's some close-up diagrams of the same thing. Once again, theta 1 is still given by 1.22 times the wavelength divided by the aperture here, which is the same as the lens diameter. I should have specified that. So the act of passing light through the lens is much like passing it through a circular hole, if your lens has a circular shape. So previously, capital D was the diameter of the hole. Now, capital D is the diameter of the lens. And now we get to the point that's, or the part that's relevant to this chapter and a couple of homework problems. This is what your book refers to as the Rayleigh Criterion. So imagine now that you're using your lens to image two separate objects. For now, you can think of them as stars, two faraway stars. And both of these stars are producing spherical wave fronts, but stars are very far away, light years away. And so by the time those spherical wave fronts arrive at the lens, they look like plane waves. And we already know what happens when you pass a plane wave through a circular aperture. You get the circular aperture diffraction pattern. So let me go back a few slides right here. This pattern, this is just one circular aperture diffraction pattern that you would get from a single source really far away. So off to the left here, infinitely far away, is some point source of light that's sending out spherical wavefronts. Oops. By the time those spherical wavefronts arrive at the hole, they look like plane waves, and you get this circular aperture diffraction pattern. Remember, laser pen. You can put a laser pen just a couple inches from the hole, and it will produce the same pattern because the incoming laser light is like plane waves which were emitted from some object far away. Okay, each of these sources will produce its own circular aperture diffraction pattern on the screen. So what you're looking at is the overlap between those two circular aperture diffraction patterns. This would be the central maximum, the center of the airy disk coming from this source. Over here would be the center of the airy disk coming from object 2. And you can imagine, look how closely overlapped these patterns are. Here is the circular aperture diffraction pattern from a single source, and I'm reminding you that if this airy disk has a width W, then this distance would actually be W over 2. So I've got a better graphic in a moment, but here's what it might look like if you were looking through a lens at two faraway objects whose circular aperture diffraction patterns were overlapping. You can just barely tell that these are two different sources. How come you can just barely tell? Because the distance between their centers, this is the center of one airy disk, this is the center of the other airy disk, it is the same as half the width of one airy disk. Can you see that? Like, let's look at this airy disk. From here to here, that's about the half width. Have I done that right? No, you know, I think I should have labeled this W. Yeah. Okay. Well, so much for this slide. I'm gonna have to go back and fix this. This is really more like W, isn't it? Not half of W. This is slightly better. Okay. Yeah. This is the condition for marginally resolving 2-point sources of light. What does it mean to resolve 2-point sources? It means you can actually tell that they're separate. You can distinguish them as two separate point sources. So look carefully at this total intensity pattern. From here to here, that's the half width. And can you see that that's basically the same as the separation between the centers of the two airy disks? So when the separation between the centers of the airy disk is equal to the half width, you can just barely tell that those are two separate sources. In other words, you are able to resolve them. So that's what I stated here in words. The distance between the centers of the airy disks needs to be equal to the half width of one disk. And you know, this definition is somewhat arbitrary. This was the definition suggested by Mr. Rayleigh, I believe in the early 19th century or mid 19th century. So that's the criterion that we'll go with for being able to resolve two objects. Here you can see that the separation between these two airy disks, or the centers of the airy disks, is even less than the half width of a single airy disk. And if that's the case, those two blobs of light look like just one blob. So it's impossible to distinguish the two. Okay, so to contrast these three examples, if we go back to, here we go. This angle alpha, that is the angular distance between the objects as seen by somebody at the center of the lens. So let me rephrase that. From the point at the center of the lens, alpha is the angle subtended by the two objects that are very, very far away. You could also say that it's the angular distance subtended by the centers of the airy disk on the screen. It's the same angle. That's a really important observation. Alpha is the same on either side. Okay, so if the two objects subtend an angle greater than that minimum, and I'm calling it theta min because that corresponds to the first couple slides. That's the angle at which the light intensity from a single disk would go to 0. As long as alpha is greater than that angle at which the light intensity goes to a minimum, you can consider the objects resolved. Crossover point is when they're equal. That's marginal resolution. This is the Rayleigh criterion. And if the angle between them is any smaller, then they're just going to look like one blob. So once again, I've gone into Python, and this time I told Python to construct two circular holes and have a bunch of point sources within each hole. And I told it to send out waves from every point within the hole, sum up all the waves, and find the total amplitude at every point along the screen, square the amplitude to get the intensity. In other words, you're seeing the pattern of alternating constructive and destructive interference on a screen where the waves are coming from two circular apertures. And I picked the separation on purpose so that the two airy disks would be at just the right separation. So let's see here. This is the center of one airy disk. This is the center of the other. Width over 4. That means the total distance between these centers is W over 2. Right, and remember, W is the full width of one airy disk. So these two point sources would just barely satisfy the Rayleigh criterion. You'd say that they are marginally resolved. If you put those concentric patterns of light any closer, they would kind of merge into one blob, and you'd say that you would not be able to resolve those two. And one of the most practical and interesting applications of this is in astronomy. Maybe you're aware that when you look at the night sky, if you go out into the desert, there are thousands of stars that you can see. In the middle of Long Beach at night, maybe you only see a couple dozen, but there are thousands, maybe even tens of thousands of stars visible to the naked eye when you're in a dark place. And you may not have realized that something like half of all of those stars are actually a pair of stars, but your eye is unable to distinguish the two. For instance, in the handle of the Big Dipper, Alcor and Mizar, I'm guessing it's pronounced Mizar, they just look like one point of light to most people's eyes. I think some people have good enough vision where they can barely tell that it's two different stars. But if you were to look at that same point in the sky through binoculars or certainly telescope, you would have no trouble telling that it's actually two stars. And evidently that's the case with something like half of all the quote stars you see in the night sky. That star is actually two stars. And in many cases, if you zoom in even further, one of the pair is also a pair. So we're not aware of that because of the limited resolving power of our eyeball. So here's a high definition photograph of those. This is probably taken by some telescope above the atmosphere, maybe the Hubble telescope. And remember, stars don't actually have spikes on them, right? Like in Twinkle Twinkle Little Star, or the star in Pinocchio. These are actually artifacts caused by the wave behavior of light as it passes through the circular aperture of the telescope. So what you're seeing here is an artifact of diffraction. Okay, now let me go back to the formula here for the width of an, you know what? That's going to come up in a future slide. Okay, so let's look now at a problem from your chapter. This is 44, I believe. Let me pause. I've been talking about resolving two-point sources of light like faraway stars through the lens of a camera or a telescope, but the same reasoning would apply to your eyeball. True, your eyeball is a spherical refracting surface in conjunction with the lens, but you can still think of it as just a single optical element like a lens. And in this problem, number 44 from chapter 35, these, instead of two stars, you're talking about the headlights of a vehicle, and this vehicle is at a great distance from your eye. And you're supposed to figure out what's the greatest distance L? How far away can that car be so that your eye can just still barely resolve the two headlights? Of course, if you put that car 50 miles away, let's say it's a very flat freeway for 50 miles, so you actually could have an unobstructed view of these headlights. At that distance, those two headlights will be indistinguishable. They'll just look like a single headlight. But if you get the car close enough, you'll be able to resolve those two sources of light. And the idea is draw a ray. Remember, this headlight is sending out rays in all directions, and a whole bundle of rays is refracted by your eye and focused to a single point. But all we have to draw is the single ray that goes through the center of the lens, because we know that that's the undeviated ray. That's all we have to do if we want to see where the image of this point shows up on your retina. So remember, from this headlight, for instance, there is a ray that comes out in this direction. It refracts at your cornea and strikes the retina at the same place where this ray strikes. But we only need this ray to see where that image forms. Okay, so you're going to get an image of the first headlight here on your retina, but you'll notice that instead of drawing a point, I've drawn concentric rings, because we know that the waves coming from that headlight are actually going to diffract through your pupil. So you do get a circular aperture diffraction pattern. We don't normally notice that. When you look at a faraway light bulb, you don't perceive those concentric rings. And that has to do with the size of your rods and cones, the light sensitive cells in your retina compared to the width of that airy disk. But the idea is, in order to be able to distinguish these headlights as distinct, the airy patterns or the circular aperture diffraction patterns from these two sources need to be sufficiently separated. I think you can tell from this diagram, these are more than separated enough to distinguish the two. So let's keep in mind that the eyeball is about 2.5 centimeters in length. And if you think back to circular aperture diffraction for a single hole, L is actually the letter that we used from the hole to the screen. So the hole now is your pupil and the screen is the retina. And that distance L is 2.5 centimeters. I've actually used the capital letter L for a different purpose in this diagram because that is what your book does. So right now we're using L as the distance from the headlights to your eyeball. But if you think back to chapter 33, L would have been more appropriate to use as the distance from pupil to retina because that's really from the hole to the screen. Okay. And you have to observe that this angle, of course, is the same as that angle. They're vertical angles. And we can easily calculate this angle in terms of how far apart the headlights are and the distance from the headlights to the pupil. So here's the whole idea. And I've got a couple other sketches here. The whole idea is that we need this angle to be greater than or equal to theta min. Theta min is the angle from the direction to the center of the airy disk and the direction to where you get the first dark spot. So I've actually drawn these bold dots to represent the airy disk. That's where the light is most intense. At the very boundary of those dots is where the light would fall to a minimum. And that angle between those two directions, that's what we call theta min. So the Rayleigh limit, or the condition for the Rayleigh criterion, the condition for marginal resolution of these 2 point sources is that this angle alpha needs to equal theta min. Well, all we have to do is quote the result from before. That's from chapter 33, diffraction through a circular aperture. And don't forget that since the wave interference happens in here, this is where those outgoing waves will overlap and interfere. That's within the eyeball. So we need to use the wavelength within the eyeball. And all you do is take the vacuum wavelength, I've denoted that by lambda naught, and you divide it down by the index of refraction. Remember, anytime your wave passes into a region where it travels more slowly, the wavelength is going to get shorter. And you calculate that wavelength by dividing by the index of refraction of the material. Now your eyeball's got two different fluids. There's the vitreous humor and the aqueous humor, but I guess when you take an average, it's something like 1.33. You know, suspiciously, that is the index of refraction of water as well. So let's take a look at a couple lame sketches here. Remember the pupil here. Think of this as the pupil. It's got a particular diameter. In this problem, it's 7 millimeters. When your light passes through, remember this ray is perpendicular to the wave front. So you've got a plane wave coming from far away, and when it hits this aperture, it's going to diffract through. So you've got all these circular wavefronts coming out in this direction, if we're talking about this source. And forget about that for a second. All of the little wavelets coming out of here are going to interfere in such a way that you get a circular aperture diffraction pattern here. You've also got another incoming plane wave here that will diffract through the hole. Now you've got a whole bunch of circular wave fronts emanating here from this source. They all interfere in such a way that they make a circular aperture diffraction pattern. Now these are obviously resolved. These patterns don't really overlap at all, which is why instead of calling this theta min, I just called the angle here theta. But the Rayleigh criterion refers to a situation more like this. So it's not a great drawing, but you can imagine that the airy disk here almost overlaps with the airy disk from the other source. And now I can call that angle theta min. That's the minimum angle alpha at which you're able to resolve these two. So let's now finish the problem here. Let's see, I could use the geometry of this diagram here. Okay. So first of all, let's calculate theta min. Theta min, remember, is 1.22 times the wavelength divided by capital D. What's capital D again? That's the diameter of your circular hole, which in this instance is the pupil. Now, alpha here, remember that relation between arc length, let me use this paper, radius, I'll call this d theta, and ds. Remember, ds is equal to r d theta, or d theta is ds over r. Yeah, you just take arc length and divide it by radius to get the angle in radians. And that's what we're doing here. This may not look like a little piece of arc length from a circle, but remember, this angle in my diagram is grossly exaggerated. These two headlights are very far away, so we're talking about a very small angle. Your book solutions manual refers to the distance between the headlamps, which is what, a couple feet, few feet? They're calling that delta x, and they've used the letter L in this problem as the distance from your pupil to these distant headlamps. So can you see arc length divided by radius, so to speak? That angle alpha in radians would just be the distance between the headlamps divided by the distance to the headlamps. What was I doing in this problem? Okay, right here. So I'll rewrite that here. Alpha is delta x over L. For marginal resolution, alpha needs to be at least as big as theta min. And some of you, I think, I got an email from a couple people, you were a little confused. You thought that you had to use the index of refraction in here to account for the fact that these rays would bend. This problem really has nothing to do with that. Now, you are correct that if you look at the various rays coming from one of these headlamps, let me get it into, there we go. I can draw a bunch of rays here, which actually intercept the eyeball. But the idea is all of these rays are focused to a point. We only need to draw this undeviated ray to see where the image is located. So you're right, there is refraction here, but that's not what this problem is about. We just assume that the angle between this undeviated ray and this undeviated ray is the same as this angle alpha. The only reason we need the index of refraction is for this. The wavelength in the eyeball is the vacuum wavelength over the index of refraction. Okay, so if we set these equal to each other, we've got distance between the headlamps divided by the distance to the headlamps. That's got to equal 1.22 lambda. Well, that's lambda naught over n, all of that over the diameter of the hole being your pupil. And what are we solving for? L. How far away can these headlamps be, okay? Or can the car be? So if I solve, I get dn delta x over 1.22 lambda naught. And I'm sorry if that was out of the screen there. And they suggest a pupil diameter of 7 millimeters because this is supposed to be at night, and we know that in the dark our pupils widen. I'm sure some of you, well, you all know what this is like, right? When you're sleeping, your eyelids cover your pupil, so your pupil is probably dilated. If you walk outside when you're still waking up and your pupil's still wide open and the sunlight hits it, it's almost painful. So 7 millimeters would be 7/1000ths of a meter. Let me check that we're supposed to go with an index of refraction of 1.33. Yes, basically water. And we're told that the headlights are 1.2 meters apart. They say 120 centimeters, so 1.20 meters. And then they give us the vacuum wavelength of the light. It's basically reddish light, 600 nanometers. That is not the wavelength within the eye. That's the wavelength in vacuum, but we've already adjusted to get the wavelength in the eyeball by dividing by the index of refraction. I'm going to plop this in my calculator and we'll see how far away theoretically could this car be. And you would still be able to resolve the headlights. See how the 1.22 and the 1.2 basically cancel. Okay, according to my calculator here, over 15,000 meters. Let's just call that 15 kilometers. That's something like 10 miles. Is that realistic? 10 miles? A car 10 miles away, and you could still tell the two headlights apart. I think we know that in real life that doesn't happen because your eyeball is not always, as your book puts it, diffraction limited. The idea is if there were no other optical issues here, we didn't have to worry about the fact that your cornea may not be perfectly curved. There's atmospheric turbulence between your eye and the headlamps. There's the chromatic aberration and spherical aberration of your lens. We haven't talked about that yet. So if you could eliminate all those other concerns, but the only difficulty here was diffraction, then theoretically you could see, as far as 10 miles away, you could actually distinguish these two headlamps. Okay. Well, let's look once more at the formula. How could you improve this scenario? If you wanted to be able to put this car farther and farther away, and still be able to resolve the two headlights, one thing you could do is make your pupil bigger. Well, we can't do that. We're kind of stuck with the pupils we've got. But if you were imaging this car with, let's say, a telescope or a zoom lens and not your pupil, you could just go with a larger aperture. It seems that bigger is better when it comes to the aperture of an optical instrument. To get better resolution, you need a larger aperture. So in a second, we'll look at an extreme example of that. Also, just have the two objects farther apart, fine. What about this? The vacuum wavelength. In order to increase the distance at which you could still resolve, you could make the wavelength shorter. That's interesting. That would suggest that if you were to image something in the ultraviolet part of the spectrum where the wavelength is shorter, you could get better resolution, or you could still distinguish those features even if they were farther away. What else does this suggest? Let's say that you're looking at something, I don't know, 100 light years away. So the distance to that object is fixed. If you're going to do astronomy and image things in a longer wavelength, the longer your wavelength is, the bigger the aperture would have to be. A lot of astronomy is done in the radio part of the spectrum, and radio wavelengths are very long compared to optical or visible wavelengths. So as you make this denominator bigger with those radio wavelengths, you would also need to make the numerator bigger so that you can still image something at a particular distance. So radio telescopes, it seems, would have to have very large apertures, and I'll show you an example in just a second. Back to visible wavelengths like 500 nanometers. In the numerator of that expression was that capital D for the aperture of your lens. That is the whole point of having large binoculars. I've got a pair of binoculars at home that are nowhere near this big, but they're still, I think there's something like 7 centimeters across the lens. That's way bigger than your pupil. Even when your pupil's fully dilated, you're talking only about something like 7 millimeters. And so if you know the diameter of these lenses is much more than 10 times that, it might even be 100 times that. So presumably you could resolve those two headlights if they were now 100 times as far as the resolution for the naked eye alone. So many people are under the impression that the sole function of a telescope or binoculars is to magnify. That's the first question most people ask is, what's the magnifying power of your telescope? And while that's significant, the resolving power is also very important. It doesn't matter how much you magnify something. If the resolution is poor because of diffraction, then you're not going to get a very sharp image. So there's really two reasons to have large lenses or large mirrors. They gather more light, which allows you to see fainter objects, and they have better resolving power. To see that, you just look at the formula for the Rayleigh limit. Okay, I mentioned astronomy done with long wavelengths. Sometimes they talk about doing astronomy in the millimeter part of the spectrum. I hope you remember that for visible light, the wavelength is something like half of a micrometer, 1/2 of a millionth of a meter. Your hair is 50 micrometers thick, give or take. So 50 compared to 0.5, we're talking about hair being 100 times as wide as a wavelength of visible light. A millimeter wave, that's much larger. I mean, normally we think of a millimeter as small, but a millimeter is a rather large or rather long electromagnetic wavelength. So some radio astronomy is done in the millimeter part of the spectrum. The Arecibo array, I think this is in Puerto Rico, but look how large that aperture is. That looks like a football field to me. You can Google that, but this is capital D. This is the capital D that you plug into the formula. And that capital D needs to be a big number because in the denominator is a larger lambda. And this is really a mirror. Hopefully you got some practice with those concave mirror problems. This is a concave mirror that reflects radio waves, not visible light waves. It's a lot like the cosmetic mirror, right? You may have a suspicion what this is all about. All of the parallel rays coming in from deep and outer space, they're all being focused right here. So this is the detector. This is the part of the instrument that gathers or collects the electromagnetic energy. And you know, if you go back to chapter 34, if this was a regular mirror and you put your face right here inside the focal point, you would see a virtual image of yourself way back here. But that's not what this is for. Really, this dish is creating a real image at the focal point. So they put the detector at the focal point, and then of course these cables are carrying the data back over here where they're processed by computers. Okay, what can you do with a telescope like this? Well, here's another example. If you want to go even bigger than that, what you can do is construct dozens of radio dishes. And these couple dozen satellite dishes or radio telescopes act in concert as if they are one giant telescope. Obviously, there's some practical difficulties in building a telescope that's like, you know, a mile across. That's a lot of material. Sounds super expensive. Maybe you'd have to just move too much earth to accomplish that. So I've never looked at the calculations in detail, but I'm aware that even a couple dozen dishes like that can do a really good job of approximating one giant dish. So this is the ALMA telescope array. I believe that stands for Atacama Large Millimeter Array. Millimeter because they're looking at light with a wavelength of roughly 1 millimeter. That's in the radio part of the spectrum, much longer than visible light waves. This is down in Atacama, Chile. It's a high altitude, which means less atmosphere that you have to look through. And in 2014, as I recall, this array produced the first image of its kind. There it is. What the heck is that? Well, we just talked about diffraction, so you might look at that and think, oh, that must be a circular aperture diffraction pattern. That's actually much cooler than that. I think I showed this in class. That is an image of a primitive solar system. At the very center of this protoplanetary disk is a new star. Nuclear fusion recently began. I don't know, maybe it's just 1 million years old in this image. So there's that nuclear furnace at the center of this enormous cloud of dust and hydrogen gas. And then what's with all these concentric rings? Those are not diffraction rings. Those are the paths cleared through the solar system by newly formed planets. I look at our solar system. Most of the gas and dust has already been removed from the solar system, and what's left is just the planets in their orbits. But you can see that there have to be orbiting planets here. What's remarkable about this image? Well, you may not have seen this before, and before 2014, no such image existed because let's think about it here. Our solar system, how long does it take light to get from the sun to Earth? 8 minutes. If you want to send a radio signal to Pluto, I think that takes a good hour or 2 hours. So we're talking about a light hour. A light hour is the distance light travels in 1 hour. That's a very large distance. But this solar system that we're looking at, off the top of my head, I don't recall, it's probably dozens of light years away. So let me just go to my notes again. Blank paper. Here's your protoplanetary disk. Star at the center, planetary tracks. Here's planet Earth way over here. I'll call this angle alpha. I'll call this delta X, and this is L, just to be consistent with the solution to chapter 44. Delta X over L. Well, I'm just using our own solar system for reference. I know it takes an hour or two for radio signals to go from the sun to the Neptune region of our solar system. So that's, let's say, 2 light hours, 2 hours over this star system is easily 24 light years away. How about I just call it 20 light years? Okay, 2/20ths, that's not really the ratio because we have to convert years into hours. Let's see, 2 hours over 20 times. Well, a year has 365 days roughly and 24 hours in a day. Okay, 2 divided by 20 divided by 365 divided by 24. That's 10 to the negative 5th radians. This telescope array has a resolving power of, at minimum, 10 to the negative 5th. If you think about it, it can resolve even smaller angles because this is the angle that the entire solar system subtends. And we could see details even smaller than that. So let's go with an angular resolution of at least 10 to the negative 6th, a millionth of a radian, probably even smaller. How do you accomplish something like that? If I go back to the formula here, set theta min equal to 10 to the negative 6th radians. Well, we know that when you pass plane waves through a circular aperture, think of the Arecibo radio telescope, that giant bowl in the ground. You've got 1.22 lambda over capital D equals 10 to, I've never done this calculation. Look how simple it is. Let's figure out how wide your telescope would need to be to get this kind of resolution. I'm just solving for D, easy. Okay, so I've got 1.22 lambda over 10 to the negative 6th. All right. Well, what's the wavelength? It's all in the name, ALMA, Atacama Large Millimeter Array. I'll just go with 10 to the negative 3rd as my wavelength. And 1.22, that's so close to 1, it's trivial. We're just trying to get an order of magnitude approximation here. So 10 to the negative 3rd over 10 to the negative 6th, there it is, 1 kilometer. That makes so much sense, because when you look at the picture here, it's tough to get a sense of scale, but I think we are talking about distances on the order of kilometers. Certainly bigger than a meter, bigger than 100 meters. This is longer than a football field, but we're probably not talking about 10 kilometers. That would not even fit in this picture, from side to side. So it's remarkable how simple it is to arrive at that number. All I'm using is the Rayleigh Criterion, and it all boils down to diffraction through a circular aperture. So if you understood all that stuff in chapter 33, you can appreciate what's going on here. And the last comment I'll make, I wish I had a graphic for you, but you remember last year, was it the year before? They did some more detection of gravitational waves, 2 black holes colliding, and some graduate student, I forget her name, but she came up with the algorithm for taking telescopes all over the world and getting them to act as a single telescope. You're looking at a picture here of just a little patch of one desert. What if you could take telescopes on complete opposite sides of planet Earth and get them all to act together as one big telescope? Then your aperture diameter, D, would be the diameter of the Earth. But there's some huge technical challenges there, and you have to deal with the fact that the light waves are going to reach these telescopes at slightly different times. And when they share information, that information has to travel over cables, and there's all sorts of delays there. So no trivial technical feat, that's for sure. But There's an acronym for that whole method, and it escapes me at the moment. Hang on a sec. This is the acronym that escaped me. VLBI, very long baseline interferometry. Now that I've turned you on to the subject, I'll let you read on your own.